Hey guys. All right, so let's keep talking about waves. Last lesson was wave equation. How can we quantify some of the relationships waves? But we still haven't really delved into what makes a wave and what are some of its behaviors. So let's talk about that here. Let's talk about the properties of waves. All of this is going to be based on one big idea, which is called Huygens principle. So Huygens principle is a way that we can understand how waves behave. It was named after a Dutch physicist, Christian Huygens, very important physicist from, well, natural philosopher at the time. The term physicist never existed at that time, but he was interested in optics, all kinds of things. In the 1600s, he made very good lenses, best telescopes of the time. But his idea here states that if you have a wave, let's say, at this point, let's pick this point here. This is going to be a pool of water. I'm going to drop a marble into the water there. And it's going to make a wave, and it's going to spread out this ripple. You drop it in the water, it's going to make this circular ripple, symmetrical ripple. And it's going to have a wave front. That's going to be this red line. That's going to be the wave front generated by dropping the rock. We can consider that wave front be made up of an infinite number of new point sources. Like I'm dropping here, these 5 dots on here can represent by 5 new rocks being dropped in there. And each of those dots is going to generate a new wave traveling forwards. We're just going to use the half because of the half. We're going to ignore that part. It's going to head forwards, and it's going to make these new waves. And you can imagine, well, if I have these 5 dots, it's going to be this funny, weird pattern of these 5 different waves interacting with each other. But we're actually really thinking that this line is made up of an infinite number of these dots, and it's going to make a whole bunch of these new waves. And they're all going to pile up onto each other to make a new wave front that's going to travel outwards like this. So the whole wave front, or the wave ray in this case, this arrow, is going to be traveling with the whole wave. So the whole wave is going to propagate by producing these new waves. Okay? So instead of here, in this example on this right-hand side, this is a plane wave. This was a circular wave. This is a plane wave. It's a wave traveling in a line. You can now imagine a whole bunch of new point sources along there, and each of those point sources is going to make its own waves, right? And they're all going to line up and make a new wave front as it travels. So as all of these waves get bigger and bigger and bigger, right? All these new point sources go out symmetrically outwards. They're going to continue to make this wave front as it propagates, and then we can do the same thing. Put a whole bunch of new point sources on there, and then they're all going to build up, and our wave is going to continue to travel along. Okay, so this is one way we can think about how waves move. The wave continues to build new waves, a whole bunch of them. They're all going to build up onto each other. Here's a good word here: superimpose. They build up onto each other. They stack on top of each other to produce the new wave as it moves. Propagate. That's a fancy word for move. Okay? Awesome. And we're going to continue to use this Huygens principle all over the place. Okay? So, first thing we're going to talk about, second thing we're going to talk about here is how waves reflect and refract. You guys are going to remember this from grade 10 with light. And light is a wave. Light behaves like a wave. Its frequency is very, very high. Its wavelength is very, very small. Speed is incredibly fast, but it's still a wave. It's electromagnetic radiation vibrating up and down. It's the interaction between the electric field going up and down and the magnetic field going right angles to that, and they're interacting with each other, going back and forth, going up and down, the other one going side to side and building on each other, and they make a wave. So when we talk about this, this is all going back to grade 10 optics. When a wave reflects off of a surface, it's going to bounce off at the same angle, which makes sense. If I have a surface here, normal, I'm going to strike the surface, it's going to bounce away at the same angle. It's an angle, reflected angle, I is equal to R. Nope, that's not a vector. I is equal to r as an angle. Okay. And also we talked about refraction in grade 10. Remember Snell's law? When a wave goes into a new medium, and that medium is either denser or less dense, that means is how much does it allow the wave to travel through it, it's going to cause it to bend. Now this is difficult to visualize, so let's jump over to a little simulation here. These simulations are all on the Weebly, so you guys can play as much as you like on them. But here we're showing what a laser looks like as it hits some medium here. So let's start with water here. Actually, let's go super dense. Has a high index of refraction. Do you remember that term, index of refraction, from optics? And let's start off incident at 90 degrees. Okay. Notice the wavelength. Normal here for a second. Almost not going. Oh, there. Now notice this wavelength. So as it reaches this medium, it's more difficult to get to. This is more dense optically. So the waves squish together. And the only way that they can squish together like this and still maintain the same frequency, because it's still the same color. The color is defined by the frequency, and we know that F equals V over lambda. So for us to maintain the same frequency and have the velocity reduced, the wavelength has to be reduced as well. Okay, so that's the first step. First thing about waves is when they reach a denser medium, they have to slow down. Think of it like the waves have to squish together. Think of it like like trying to walk through water. Right? It's harder to get through, so you walk at a slower rate. Okay? Now, what that means for these waves is if they're hitting at an oblique angle, like, notice what happens. See how these waves, they still have to be smushed together, but the waves still have to be continuous. We can't have a break. We still may have to maintain the continuity of this wave front. Okay, this line here, then all of these wave fronts still have to line up to each other. And the only way that we can satisfy those two conditions, first condition being the waves are squished together, and the second condition being that they're still continuous, maintaining a continuity of wave fronts, is that the whole ray has to bend. Notice this ray is coming in at this angle, this incident angle here, and then it's being bent towards the normal since it's going into a more dense medium. Hopefully you remember these things in grade 10. If not, maybe freshen up on Snell's law. Okay, and you can see it has, as we change angle, increase the amount of bending. Also, what's nice in this little simulation is it shows that the incident angle and the reflected angle are the same. Notice that it never fully goes into the medium. There's always parts of it. You can actually take this little intensity meter, and it shows me that 75% of it's going in and 25% of it is bouncing off. Okay, 100% of it, 75, 25. And there's actually some very interesting physics about how these things happen, which way the light is polarized and how they reflect off of things, how polarized glasses help us see in water, but we'll talk about that in grade 12. Okay? And you can actually play with this, and we can change it to go the opposite direction. To go from a dense medium to a less dense medium, the opposite is actually going to happen. It's going to bend away from the normal because it's speeding up. So notice, see how these waves are all compressed together? Now they're going to be stretched apart, and for that to maintain the continuity, we have to bend in the opposite direction. And we end up actually with total internal reflection, which is a term I hope you remember from going into the medium, but once we get to a certain critical angle right there, we end up with the awesome that is a wonderful website. University of Colorado provides all these free simulations. They're all awesome. Go play around over there. If you're bored during your quarantine. So this is my critical angle. I can switch over to ray to see it better. It's about 50 degrees. Okay. You can calculate that using Snell's if you want. Okay. So there's two things. Light bends when it changes medium because it has to slow down, and when it reflects off of a surface, it has to reflect at the same angle in which it's incident. Okay. Let's head back. Okay. So reflection or refraction. Here we can see again another fun thing you can play with also on the website. This is another fun simulation. You can actually watch. There it goes. So you can see the wave as it reaches this medium. It propagates through here, and at this point, because it's reaching this denser medium, it has to squish together. The angle changes. Part of it is also being reflected away. Okay, this is a great website as well. It's also on the Weebly. Play around with a bunch of stuff. I will play with it a lot, actually, in this whole unit. Next one. What happens when these hit these mediums? Does anything else change? And the thing that changes is the phase. If you go from a lighter medium to a denser medium, like from air to water for optics, or from a light slinky to a heavy slinky, or a light string to a heavy string, that place where they meet behaves as though it's a stop, and it has to bounce off of there. And when it bounces off of there, it actually reflects its phase. If the wave reflects off a denser medium, it flips its phase. The one that travels through slows down, and it wavelength actually decreases. Sorry, that's a mistake there. The wavelength actually decreases. All right, and again, I have another simulation from PhET where you can actually see that as we send a pulse at a fixed end, it will actually flip its phase. So remember, phase is the direction in which the wave is traveling. So in this case, I'm sending it in the positive direction if that's up, and then it's going to bounce back in the negative direction, which is down. Okay. Now, if this was a loose end, now that behaves like as though nothing happens, right? So this one goes up and it comes back in the same direction. A fixed end, it bounces off and it flips its phase. Anybody know why? You guys think about why? Think about Newton's third law. Okay? When Newton's third law, when it reaches this point, compared to Newton's third law when it reaches this. Okay? Won't answer the question. I'll let you guys think about it. All right? So let's stop these simulations. All right, so when it reaches a denser medium, it flips phase. That's the most important part here. Okay? When we reach a dense medium, we have to flip our phase. Last one we're going to talk about, diffraction. This is the reason why you can hear somebody when you can't see them. If you open up a door and you don't see your mom, let's say, and she's calling for you, you can still hear her because, well, one, the sound will bounce off, but it'll also be able to travel through the aperture, which is the door. It's actually able to bend through. So, an example here, I have an aperture, I have a hole here where the waves are incident on. But instead of the waves only traveling in sort of like a tube, they're actually spread outwards. And this goes back to Huygens' principle. Okay, at this point, we can imagine a whole bunch of point sources, and each of those point sources is producing a wave. So the ones that are down in the middle there, here, they end up producing what looks like a plane wave. But the ones on the outside are producing circular waves. So they end up actually producing waves on the outside. So we end up having, instead of just the waves traveling down through this tube, we have all this diffraction. It spreads out. Waves spread out around an aperture. They're able to bend around the outside of a barrier. Instead of, imagine if I had water coming in and it hit this barrier, we would have this tube of water coming through. But instead, it's able to spread out. Okay? Let's go back to that little ripple tank here. And if I go and let's just have a gap here, and I start it, you'll be able to see this phenomenon. Okay, so I have the little gap in there, and the waves are able to ripple out here. Now, there is an interesting feature here, though, about what happens if I reduce this frequency to a frequency that's almost the same as the gap. I get a very large diffraction. The most diffraction happens when the wavelength is similar to the, and what I mean by that is, okay, let's go at a high frequency. Most of the diffraction happens along here. We can flip it over to a three-dimensional view, and you can see that a bit better. Most of the diffraction happens on in this sort of triangular shape here. And go on the site. It's on our Weebly. Play around. It's a lot of fun. Okay, so where am I? So most of the diffraction happens in that triangle. But if I reduce the frequency so that the wavelength is similar to the aperture size, the diffraction gets much, much larger. Here, this is almost the same, and as you can see, there's diffraction all the way out here. If I flip it over to 3D, you can see that diffraction is much, much more pronounced. But another interesting feature is if I reduce this aperture width, let's make it like 50 or something, make it a very small aperture, much smaller, the waves can barely get through. If the aperture size is much, much smaller than the wavelength, the waves are unable to get through. And this is why you're able to stare into your window on your microwave and not get your face cooked. The microwave window has a metal screen in front of it with a bunch of holes. The holes act like this aperture here, and light is high frequency. Light is a very, very high frequency electromagnetic wave. So it's able to, still not enough. Let's make it a little bit bigger to show you the relationship. So for light compared to the hole, light would see the hole like a 400%. Pardon me. So light would see it like this. So light has no problem getting through. We're able to see the image on the inside, no problem. Okay. However, with excuse me, with was it? I think I had 50. With the magnetic waves, the microwave radiation has very, very long wavelength. The microwave radiation is in the order of tens of centimeters, and that wavelength is unable to get through that gap. Okay, so the waves, when the wavelength is much larger than an aperture, nothing gets through. If the wavelength is in the same order, it's able to get through no problem. Okay? All right, so diffraction. What do we say about diffraction here? It's when waves encounter an aperture in a barrier, they bend around the other side of the barrier. All right, so we have a bunch of new words here. Reflection, refraction, propagation, phase, reflection, of what happens to the phase when things reflect, and diffraction. We defined all these terms on lesson 1, but hopefully these clear up some of the confusion with. All right, so here's some problems 1 through 5. I'd like you to work on those, and good luck, and take care of yourselves. Remember, 3 rules: stay safe, stay home, do physics. Take care.